Roger-Young arc algebra, something like that. Yeah, yeah, yeah. And I end at 11.
Somebody
Okay.
lost it.
I lost this. Okay.
Yeah, so maybe make
Okay, sure. So we will start in few minutes. So we found a card with the number 503, which somebody forgot somewhere on the.
Lost and found.
Oh, sorry, that's mine.
Right.
It fell in my pocket. Thank you. Thank you so much.
So we continue the success story with the next talk of Professor Wong on the Roger-Young's arc algebras. So you're welcome.
Thank you to the organizers for the invitation. It's been really, really fun to be here and to listen to all this wonderful math. So I'm going to be talking about the Roger-Young arc algebra, and in very many ways, my talk will be the mirror of Adam's talk, but with a different arc algebra. So this is all joint work with Han-Bom Moon. Who's an algebraic geometer at Fordham University. So here's the plan. So I want to define the arc algebra, and then I want to spend some time convincing you that the definition is the right one. And some theorems or details, a little bit more details at the end. All right, so here's the definition. Well, actually, before I need some definitions. Okay, so this arc algebra is for closed oriented surfaces, and I need for here at least one puncture. Okay, so for example, like here's a torus with two punctures. Okay. In them, I'm going to be talking about framed links, and the framed links in a thickened surface. To me, the thickening is just so that I have room for over and under crossings. Okay, so for me, I think of them as diagrams. So that have over and under crossing information. Okay, so and this is exactly the same as for skein algebras. For these diagrams, I think of them. I allow Reidemeister 2, Reidemeister 3. But not Reidemeister 1. So for example, there, I've changed my link. Okay, that's a different link. Okay. In this algebra, like I said, there's also framed arcs. And again, I think of them as pictures. Okay, so for me, the arcs is a picture that goes from one puncture to the next. We can come back to the same puncture, and again, it has over and under crossing information. So for example, here's an arc. Oops. And when I come back, I should come back at a different height. Okay, so I think of these as crossings at the puncture. Okay, so there's, again, on the interior crossings, I have the same Reidemeister moves R2 and R3, but not R1. In addition, at the, there's extra, if I have a crossing at the end point, so I have kind of like a half of the Reidemeister 2 move, right? So I think of that as half of the Reidemeister 2. And in addition, if I can unwind around the puncture, so these two are exactly the same. Okay. All right, so let's see, I did some pre-drawing before. So now I think I'm ready for the arc algebra. The arc algebra, so I have my, so here's my arc algebra. So to define an algebra, I need coefficients. I need to tell you the module structure, which to me, I'll tell you the spanning set and relations. And then I also need algebra, so how to multiply curves together. So for me, this arc algebra contains C Laurent polynomials, so that's the coefficient ring, linear combinations of framed I label the punctures, V1 through VP, and actually I'm going to throw in their inverses as well. Okay, and these don't really do anything. I'm going to make the punctures commute with everyone, so they're just kind of there, and they're there for geometric reasons, which I'll explain later. And then I have the skein relations. On the interior, yeah.
So it's one link and one arc?
No, I should
or
disjoint unions of.
okay. Not
So, pardon?
okay.
Yeah.
So you can have multiple components, some
Yes.
of which are links
Links
and
and
some
arcs.
of which are
Yeah,
arcs.
that's right.
Okay.
Any other questions? So my generating set are unions of these things, links and arcs and punctures as well. Okay. And I mod out by skein relations. So there's the normal, usual skein relations from the skein algebra, and then I throw in a few more. So here are the new ones. If I have a crossing at an endpoint, then, now this is a little bit weird. If this is the ith puncture, then I divide 1 over vi times, and then again, so I think of the usual one as a resolution where on the bottom I go right, and then I pick up a q plus, and then if I go left I get a q minus. It's the same thing here, except I only have half a picture. So if I, from the bottom, if I go right, I have a q, not to the plus, but to the 1/2. And then here I have q, if I go left, I have minus 1/2. And already I see I find my mistake. Here I don't want Laurent polynomials, I want Laurent polynomials in a square root because I have this 1/2 right here. So I'm going to also allow half powers. Okay? So this I really think of as half of a crossing skein relation. And then similarly, if I have a loop bounding a disk, I can remove it and put minus q squared minus 2. If I have a loop bounding a puncture, I get rid of it. Right, I still have my puncture in the middle. But in this case, I put q plus q inverse. Okay, and this was defined by Julien Roger and Tian Yang in 2014, I think, or somewhere thereabouts.
Sorry, and who's DT? DT is a new variable, or what is that? I thought it's notation for the puncture.
This VI, it's the variable that I called.
So is this a just complex number or what? Or it's a new variable?
It's just a new variable.
Oh, so the ring is bigger.
Yeah, technically, but I want to think of it as a generator instead of as something in the ring. Although to be honest, I just think of it as belonging to the ring. And I forgot to say also that the VI's commute. So that's also okay. Yeah, for algebraic purposes, I ignore them completely. And then finally, I need algebra multiplication, and algebra multiplication is just as before, I stack. Okay, so should I draw a picture? Oh, that's right. Algebra multiplication by stacking. So for example, two arcs, then I draw one on top of the other. And then I have crossings, I have interior crossings and then crossings at the endpoint, and I use these formulas to compute. Okay, so here's a remark. So in Adam's talk, his surface has boundary. And in the boundary there are marked points. So if this is the boundary of your surface, then for Adam, this is 0, right? But in this Roger-Yang, so if I had, oh, sorry about the colors. I can comes back to the puncture, a loop, this is non-zero. Is everyone comfortable with this? How I might show that it's non-zero, or would it be helpful to do a calculation? In particular, this one.
You didn't say it was 0, so why should it be 0?
Okay, I'll show it by 0. All right, so there's a crossing at this puncture, so I can resolve it, right? So let's say that's V1, so this is 1 over V1 times, and then there's 2 resolutions. So there's one where I go, from the bottom one I make a right turn, so this is q to the 1/2, and then from the bottom one I make a left turn, so I have q to the minus 1/2. This one is, I'm going to not draw the background, so 1 over V1, q to the 1/2. This one bounds a circle, so this is minus q squared minus q to the minus 2. And that one bounds a disk, a puncture, so that's q to the minus 1/2, q plus q inverse. And if you work this out, this is not going to be 0. It's just a puncture itself. So this is not 0. Okay. So some algebraic properties.
Can you add one word of motivation? I mean, where is it coming
Yes.
from in quantum algebra or in whatever?
That's part 2.
Okay,
Give me 5 minutes and I'm going to spend most of my time talking about that.
sure.
Okay, so some properties is commutative when q equals 1, and that's just obvious. Right? Roger and Young show that it's spanned by curves without interior crossings, crossings at the endpoints, loops bounding disks, and loops bounding punctures. That's rather obvious. Well, it's hard to prove, but it's intuitively obvious. It's finitely generated, and this is a result with a colleague and 2 undergraduates. And then also with Han-Bom, we show that there's no 0 divisors. Under certain conditions, we couldn't prove it for all surfaces. We called it locally planar for lack of a better word, but literally it means that if sigma has an ideal triangulation, say delta, then there are no 1 or 2 cycles in the one skeleton. Right, so among the edges, there's essentially few self-identifications, or no self-identifications. Okay. So now I'm going to answer Dora's question, is why is this definition the right one? And like I said, I'm going to spend almost the whole talk about this. So, why? So, Roger and Young designed this algebra and came up with these relations so that it's a quantization of Penner's decorated Teichmuller space. So remember that if you take the Kauffman bracket skein algebra, it's a quantization of the regular Teichmuller space, and this is due to work of Bullock, Kruszycki, and Sikora, Froman, Joanna, I'm going to mangle her last name, so I'm not going to say it, and Bullock, Turayev. There's a whole bunch of people that went in that story. And so literally they said, can I find an analogy of that whole construction for the decorated Teichmuller space instead? And so this is the candidate that they came up with for the quantization. So let me review what the decorated Teichmuller space is. So consists of pairs sigma with finite area. And R is a choice of horocycle, or rather a length of a horocycle at every puncture. So the idea being that if you have such a pair, you can compute length of loops and arcs on sigma. And here sigma is not thick, it's just the flat surface. So for example, let me draw some pictures. So for a loop, I don't need that extra decoration of horocycle. I just use my metric. I can get a length of k just from M. If I have an arc, well, in general they'll wind around a bunch, right? I have this decoration, and so what I do is from M and R, from R I have these horocycles, which could be big or small, right? And so the decoration allows me to say chop here to here, and so you measure from horocycle to horocycle. Okay, so that allows you to have lengths. And just for good measure, you can also have some kind of an idea of a length of a puncture as well. So literally, for a puncture, you just have this length here. Is the length of the puncture. So this allows me to define, again, an analogy with the story for Kauffman bracket skein algebra. You can have these things called trace functions. So here, generalized functions. And these trace functions are functions from the decorated Teichmuller space to complex numbers. And you get a different trace function for every loop, arc, or link. And I'm going to only define them for loops, arcs, and links, and then you can do things to get disjoint units. Right. So, so suppose I have a pair. If I have a loop K, I can take the trace along the loop K, and this is going to be just the usual trace that doesn't. You don't invoke the horocycle, so it's just e to the length of k over 2 plus e to the minus length of k over 2. And this is just the usual trace. You can think of it as the trace of the holonomy map. It's of M, okay, that along k. In addition, if you have an arc, then arcs, remember I said it was kind of half of a loop, you get half of this formula. Okay? And then if you have a puncture, I just take the length of the puncture itself. I don't do anything at all. So the length of the horocycle around there. So note that these TRK, these generalized traces, are C infinity functions on decorated Teichmuller space. And Penner showed, actually for Penner only, so this is the usual. This is the usual trace.
This is L for K. MR goes to trace of K to L.
L of K over 2.
Plus.
Minus L of K over 2.
Okay.
It's the Koch,
Yeah, okay.
whatever, yeah. So this is the usual trace. Penner, for him, this trace along an arc, he calls them the lambda length. But for my purposes, I want to think of it as a trace, so I'm just denoting it as a trace. So Penner showed that actually you don't need the knot or the puncture. You can just look at these arcs by themselves. So if E1 through En are the edges of an ideal triangulation, then I can look at these trace of E1 through trace of En, right? So if it's an edge of an ideal triangulation, it goes from puncture to puncture, so now they're arcs. I take these generalized traces, they parameterize decorated Teichmuller space, and in fact you can use it to show that the decorated Teichmuller space is homeomorphic to Rn using those coordinates, using these functions. These traces satisfy the Ptolemy, okay, I'm sure there's, this is spelled incorrectly, relations, which means that this decorated Teichmuller space is always an example when you read a paper about cluster algebras. So, So Routier and Young looked at all three kinds of generalized traces. They didn't just look at the lambda lengths, the ones with the arcs, and they asked what are the relations among these trace functions? Okay, and the answer is this, when Q is equal to 1. So the relations are exactly encoded in this arc algebra here. Let me write this down using algebra language. But essentially that's what they found, is that, and there's a lot of serious hyperbolic geometry to get these two to match up, right? So in particular, like that 1 over VI comes from the hyperbolic geometry, that there's the length of the puncture is involved when you take.
So what's the relation between VI and L of VI?
L of VI, that's the length of the Morris cycle.
Yeah. So
Yeah,
that variable VI is
yeah.
L of VI, not the exponential of the.
That's right. Let me write down the formula. Give me a second. So here's a 0. Young and 14. So they say that there exists a homomorphism from the arc algebra when Q is equal to 1, and actually I want to take the square root also to be 1, and it goes into the C infinity functions of trace, the Teichmuller space, and literally you send, and for me beta is loop, arc, or puncture, and what you do is you send it to the trace function defined for that trace. And then to get the minus signs, there's always this issue about minus signs. You need minus signs to match. You need to, for every different beta, you need a different minus sign to make it match. And there's a consistent way of choosing this. So beta is loop, arc, or puncture. And if you take unions, you have to take a product, just like you do in the skein algebra. And the C of beta is what they call the curling number. To me, it seems like something like what you need for ride, right? You want to count the number of times you go around. Okay, but on a surface. All right. In fact, they show that this is an algebra homomorphism. In fact, it's a Poisson algebra homomorphism. So there's a Poisson structure on, let's see, where should I start? On C infinity of the decorated Teichmuller space, that's the Weil-Petersen. And in their proof, they use a computation by Mondello. On the arc algebra with Q equals 1, there's a version of the Goldman bracket, so generalized Goldman bracket. So they showed that there's this algebra homomorphism. In addition, they, in analogy of this story, sitting above the arc algebra when Q equals 1, you can think of, which is commutative, when you set Q to be not equals 1, it becomes non-commutative. right? So you can think of it as a non-commutative deformation. I think the technical words are deformation, quantization. And the whole machinery, it's exactly analogous to the skein algebra math-wise. So,
Actually, I think it's the quantization without deformation. So, technically, I think deformation quantization means that everything is power series in h bar.
yes, that's
where
right.
q is e to the h bar,
It's-
and you do something stronger, so you can remove the word deformation, I think.
So yes, almost. So it's very tempting. So you want to remove the deformation, but there's a few things missing in this picture before I can do that. So for example, I don't know that phi is 1-to-1. So they conjectured that it's 1-to-1. So in particular, there's these relations, right? Are they all of them? Are there more? Right? So you kind of, there's these questions that are left unanswered. So I'm missing a few things to say that it's a quantization in the sense of algebraic geometry. So the first thing is a conjecture from Roger and Yang that phi is 1-to-1. And the second thing is that usually, so I need to identify. So I want to use algebraic geometry, right, to do this quantization business, right? There's this whole theory from algebraic geometry to quantize. But to use algebraic geometry, you need an algebraic variety, right? And in this picture, there's no algebraic variety that I see, right? So I need to identify some algebraic variety, x, so that this image, if it's 1-to-1, of the arc algebra is exactly the coordinate ring of that algebraic variety. Right? So in the Kauffman bracket skein algebra case, this algebraic variety was the SL2C character variety. In Mueller's case, Adam said that this algebraic variety was, let me get the word straight, symplectic flat C2 bundles over the sigma with the choice of section for March points. And I just copied that from his talk. Okay, so in this case, there's two things that we need to show, that it's 1-to-1, and then we need to find an algebraic variety that corresponds to that, and then we're done. Then we can say it really is the quantization.
But the dimensions match, right? The dimensions
Dimensions of
of this one and that one.
this one and that one. Well, I think they do. So, and a partial result is that I can show that it is 1-to-1, but when sigma is locally planar, not in every case.
Is there a symplectic structure here?
Pardon?
Is there a symplectic structure which could use for this deformation quantization?
I don't know.
But usually, yes.
Yes.
Yeah, I mean, this Poisson structure.
Simply is stronger than Poisson.
Yeah,
Yes,
easy
that's
Poisson.
The dimension is not necessarily even for the decorative dimensions.
Oh,
Wrong.
Yeah.
the dimension, well,
Then degenerate.
so, any other?
And character variety, so in case character variety is if you don't have punctures, if you remove punctures.
If you don't have punctures, it's the SL2C character variety. It's the same thing, right?
Then everything
Then
works.
Right, everything works, that's right. So when there's puncture, then I don't know what algebraic variety to use. In fact, actually, so I'm going to talk about work in progress. In the work in progress, we're trying to figure out what algebraic properties of this, the arc algebra I have so that I can guess what algebraic variety goes there. So let's see if I can finish that. Actually, in previous talks, I had always said that the Roger-Yang arc algebra is the quantization of decorated Teichmuller space, and Ken kindly pointed out after one of my talks that I was saying something wrong. So that was where this all came from. Okay, so here's some partial results. They're not full. So again, E1 through En are ideal edges. So in certain cases, we can show that phi is 1-to-1. So if no EI is a zero divisor in the arc algebra or the commutative version. Okay, then we can show that it's one-to-one. That's actually pretty simple. Very simple algebraic argument. Doesn't take very much work. Doesn't take very much work if you're an algebraist. So for me, it was like total different way of thinking. But for Han-Bom, it was super easy. On the other hand, we couldn't show that edges were always non-zero divisors. Okay, so we did it. At first, we did a check for a three-punctured torus, a three-punctured sphere. The usual candidates, one punctured torus. For these, it's you can compute algebra generators and relations, and you can just look at the presentation. And that follows from the work that I did with my undergraduates. Or when sigma is locally planar. And again, remember, this is no one or two cycles in the one skeleton. Sorry, I'm writing slow. Okay. Literally what this means is that if I draw, so here's a triangulation, right? And I have my edge right there, right? So what this means is that if I take the star, let's see if I can make this big enough, that among here, it's locally planar, meaning there's no self-identifications of these triangles. And that gives me control over what happens when I multiply by E. And so if I have control about when I multiply by E, then I can do it. And when there's identifications, things go really wonky and I freak out. Okay. So how much time do I have left?
Half an hour.
Half an hour, whoa. Okay,
Oh,
I'm
sorry,
going very
20
fast.
minutes, 20 minutes, sorry.
Okay, so if you don't mind, I'd like to sketch the proofs of these two. Let's see. This first one is quite easy. And then the second one is driving me nuts. Because there's a lot of case where things go wrong in ways that you don't expect. Because with arcs, because of this unwinding business, you get a lot more things can happen. So, in fact, my goal before coming to this conference was to write up the preprint so that I could have it on the archive, and I'm drowning in cases and details. But the proof is there. It's just not very pretty at the moment. Okay, so the proof for A is easy. Okay, so here's a key property from Rushing and Young, and they showed this, is that if you have this phi, it factors through the lambda functions along the EI. So I changed notation right there. Lambda I is the trace along the EI, along the ideal edge. Okay, and so they show that it factors through. You don't get all of these because I don't know how to get an arc to match to get sent to the inverse of a trace, right? One of these lambda functions, but it definitely goes through this way, right? And so, what's the idea? So these ideas. So if EI is not a zero divisor, and you can tell. And this I learned from papers of Joanna and Tong and Charlie. You can localize. What does localize mean? You can divide, right? So you can divide. You can divide by the EIs. Okay, so if S is the monomials in EI, I can consider the fractions, where I have, I want to call them skeins, but they're not quite skeins, they're arcs, right? These skeins, can I say skeins because that's how I think of them? All right, so skeins in the arc algebra, and I have over EIs, some EIs. All right, so this thing, it turns out, is exactly isomorphic to C of lambda I. So here, this is, so Let me add some color so you can see the difference. So I can localize. Oh, is that too light? That's way too light. Maybe I use blue. I localize, I get S inverse of the arc algebra. I have an isomorphism here. The localization map is 1-to-1, and then I compose and I get that it's 1-to-1. Super easy. Okay, any questions? All right, so the proof for part B, on the other hand, is a bit of a nightmare. Okay, so suppose sigma is locally planar. Like I said, this means that I have control over the resolutions of EI, E times, let me just take that instead, times the skein. Okay, so if I take an edge and a generic skein, I have some control. I don't really have control over all of the top resolutions, but I have, just like in skein, you can have a positive resolution and negative resolution. Those are really the highest weight ones, right? So you have the positive and negative ones. So suppose E is an ideal edge. I want to show that 0 E times some linear combination of Ci beta I, right, that it's non-zero. So these betas, I'll think of these as loop or arc. These C's is, like Anna wanted me to do to begin with, is I think of as Laurent polynomials with the puncture splitting, because they commute anyways, right? So really what I'm looking for is Ci E beta I. Okay? And so the worry is that when I take linear combinations, that I might have some resolutions that cancel out. And so something that's not zero, you multiply and you get 0 at the end because of some weird cancellation. In the skein case, this doesn't happen, right? And again, here it also doesn't happen, but there's just a lot more cases to worry about. And let me tell you a little bit about what I mean. So here, they solve each E beta I, and I want to say that there exists some highest positive or then negative. Here, it's probably easier if I draw a picture. So here's my edge E. And if I have beta intersecting E, then I can resolve, right? And I can use always positive slope, right? So here's positive slope. Like 1, 2, 3, 4, 3. 1, 2, 3. I'm missing 1. Is that better? No, that doesn't look great. What have I done wrong? 1, 2, 3. This is what I did wrong. There we go. Okay, this is the usual positive linear resolution, and I'm out of space. Can I erase this top part? So. If I have beta as an arc, as a loop, I have my E here. And I could have a resolution, I could have an intersection that looks like this. Right? So here's my beta, and then it goes and ends up somewhere else, right? So these are the crossings with E that I see. What I do is I do the same thing. Let's see. I do right resolution, right? So 1, 2, 3, and then I think that's it. Okay. And so if I have an arc, then I get the opposite. Okay. So again, like I said, it's only in the case of loops I never get any cancellations. But in the case of arcs, what happens is, here's the problem here, is this relation. So I can unwind, and so what happens is that a positive resolution, if you unwind, suddenly looks like a negative resolution. And so there's these things that can cancel out. And I drew a picture before. Maybe. Let's see it. So, I don't know. This is might be hard to see. So here's my E, and then here's the two triangles on either side of E. So next to E, these pictures look very, very different, right? So what I claim is that, let me attach these guys. If I attach this guy this way, and this one this way, and this one I go twice, 1, 2, and here 1, 2. Okay, so in this one I resolve, I guess that's negative, and this one positive. So let's see what happens. So here, this is going to be hard. Let's see if I can do this. I have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I resolve. So I go this way. Oh, actually, a little bit. I go. Okay, so let's see. This one will go around. Wait, did I do that right? No, I didn't do that right. This one goes to the second one. This one loops around this way, right? So ignore that part. And then here I have the middle one going here. And then this one goes here. Okay? All right. On the top one, I resolve in the other direction. Okay, let's see if I can do this. Okay, and now you see what's wrong. This one will wind around. Okay, so I wind around. This other outside one will come through here. Okay, let's see. Here, let's say I go up and around. Up and around. This outside one comes this way. Okay. And so if you think about pulling unwinding, you get that these two are exactly the same. Okay, so there's lots of little cases like that that we have to worry about. In the end, it all works out, right? I just need not only just to look at the highest weight positive resolution near E, I need to look at the whole star. And once I need to look at the whole star, that's why I need locally planar. Okay. So one other thing that I wanted to talk about in the proof that came up is, so in the case where it's locally planar, this is getting really technical, but I thought it was an interesting part of the technical stuff. So here's a technical tool that we use to describe the positive and the negative resolutions. And the technical tool is basically stolen from papers of Joanna, Tong, and Charlie. We use this thing called corner coordinates. Basically, they're the same as intersections with edges, but they're kind of nice. And so what we do is, in order to describe these positive resolutions, or any arc, in fact, any skein in my algebra, I look at each triangle, and I say, okay, how can a skein intersect this triangle? Again, I use reduced, no crossings anywhere, no loops, blah, 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 right? So you can have that every curve goes from edge to edge. You can have an endpoint at an endpoint, right? And other ones going from edge to edge. Or you can have a copy of one of the edges of the ideal triangulation. Okay? So, in this case, you don't want to use, well, so let me explain what it is first before I talk about it. Okay, so in this scheme, we use these things called corner coordinates. And in the case of loops, this is old math, right? Normal curves on surfaces. So at each of these corners, I assign a number. This one is 2, here's 1, and 1. Okay, and you can see that if you add 2 plus 1, you get the number of edge crossings, right? Intersections with the edge, and that all goes through fine. Here, when I have an arc, I put -1/2 anytime you have a loop ending there. And the way I count this corner coordinate of this coordinate is this arc counts as half of a loop, so it goes, you get a half here, and this one is 1.5. Okay. Over here I have -1/2, -1/2, and here I have 1, and then I get like, if depending on which side you get, I get another half. So this is 1.5 over here. Okay, so this is a well-defined, again, this is like I'm getting into the nitty-gritties. You can assign corner coordinates on these, and in the case that it's locally planar, we have formulas. And so, when locally planar. And the beta is a reduced multicurve. There exists formulas. So if you go from beta to, say, the positive resolution of beta or the negative resolution, and then it's just a matter of casework, lots of it. And then I think that's it. Oh, right, I wanted to say also that we have that it's 1-to-1, and in work in progress, we're trying to guess what the algebraic variety should be. So in particular, for example, Han-Bom is convinced that it's a toric variety, which is surprising considering it was not the case, according to Adam, for the SL2C character variety or for Mueller's arc algebra. So there's something else going on here that's different. Anyways, and that's it. Any questions?
Any questions or comments? So it seems that your proof of A is in if and only if.
Oh, I don't know. Is it if and only if?
Well, you factor the map phi to Laurent polynomial.
Right.
And the other one injects. So the only question is whether the map to Laurent polynomials, but if that injects if and only if the I is invertible, because that's what we're inverting. So it seems to me, but maybe I'm wrong.
Thank you for that comment.
How does that compare to the usual skein module or the extension with punctures? So we say if there are no punctures, the same thing as the usual skein module?
That's right.
If there are punctures, you have the usual skein module that goes into use.
That's right.
But
Well,
that's not subjective.
I guess you can.
It's more subjective.
You can wait. So if you have the skein algebra, right? So without punctures, right? Then essentially, I'm just ignoring the information around the Horner cycle, right? Then you inject in, and then you get the SL2C character variety, right? And it's 1-to-1. But this is bigger.
And compared to the one that Tom described, how does that relate?
They don't relate.
At all.
As far as I know. So this is an open question, because for Tong, remember, there's that teardrop shape, and that's 0, and for me, it's not 0. And in case of Tong, you have an actual boundary component with marked points. Here, there's no boundary. So I think they should be related. I just don't know how.
So then one is, the cluster theory of Wong and Thurston, you need to open up the puncture to make it into a mark point, and then do some kind of Gaussian, and then maybe there might be some connection between that one and this one. But I'm not quite sure.
Yeah. What I think is interesting is like Muller came from the algebraic side, and then like work of Adam puts the hyperbolic geometry in. This one comes from the hyperbolic geometry, and then now we're trying to find the algebra that matches it, right? So it's like going two ships being in the middle.
So when there is no puncture, people are interested in understanding, for example, at root of unity, center and representation. Are you expecting something similar?
That's too far ahead. I have no idea. But I think it would be nice if there were. So for example, I don't know what's in the center. It should be Chebyshev's, but then arcs are involved, and I don't know how that works. You can, if you allow yourself to divide by a plus a inverse, for example, then you can generate only using edges, right? And then maybe that will give you something that, yeah, that we can use. I don't know.
If there are no further questions, let us thank Helen
Thank you.
again.